Yeah, with that, please join me in welcoming Andy Patterson. He's also a PhD student here at the RLAI lab, and he's going to tell us about objective functions for learning values. Go ahead, Andy.
Yeah, so I guess the title of my talk was almost as generic as I could make it. That's largely because I didn't decide what I was going to talk about until, I don't know, an hour ago. So I felt bad. Abhishek sent me a request for an abstract and a title, and I just kind of threw something together yesterday, hoping that what I optimized for today was going to somewhat match. So I guess we'll find out. Yeah, as Abhishek said, feel free to interrupt at any time. This slide is going to show up every 2 or 3 slides. It kind of helps keeping me on track, gives you guys an idea of where we're going. So this slide is an excellent spot to interrupt me. Any time is okay, but this is the best time because this will be right after I finish like a complete thought. This is going to show up again right before I start a new, hopefully complete thought. Yeah. So dive right into it. My goal is to learn better value functions. If I put better in quotes here, better can mean a lot of things to a lot of people. So to be specific, my goal is to minimize this prediction error, is to minimize this mean squared value error. And so what I have here, I've got this hat on this V that tells me I'm learning this V, I'm estimating this quantity. It's parameterized by some values W, and I'm trying to minimize the distance between it and some true value function, if you will, some V pi. These are values that are given to me by the MDP. And so maybe to be specific, what I mean by V pi, I can write V pi is equal to, assuming I have some knowledge of my MDP, maybe V pi is equal to this, I minus gamma times this my transition dynamics matrix, and this is my, say, average reward function. So I'm trying to minimize the distance between the thing that I can represent, my parameterized value function, and this sort of true thing. And I'll talk about D in a sec. I bring this second thing up, the second definition of better, the second goal. This is actually not what I'm going to do. I'm kind of showing you what I'm not doing because this question comes up all the time when I talk about what I do want to do. Constantly people are asking me, well, if you're learning better value functions that better match this true value functions, that necessarily mean you're going to be maximizing reward when you try to turn this thing into a policy later. And the answer is definitely not clear. But that's not what I'm trying to do either. So I guess I don't really care what the answer is. Maybe this V of, I could have written this as a Q hat essay. Sorry, my handwriting's so bad. And maybe this could be showing Q learning, for instance. Or maybe this is like an active critic system where I'm using the value function just to stabilize learning of some policy parameters. But regardless, I bring this up just to point out this is not what I'm trying to do. This is what I'm trying to do. I just want to learn a really accurate value function. Great. Oh, I circled D. Yeah. So D, what is D? D is this matrix. It's this, I wrote it as a diagonal matrix, zeros here on the off diagonals. And it tells me some amount of weighting over states. So I have this grid world that I drew, and this green thing is how often my policy visits each of these states. I guess I drew this like a sort of uniform. And so what D might specify, maybe this is some S1 here, that I care how accurate my predictions are in S1 by some weighting, and all of these other states that I never visit. Maybe I don't care how accurate my predictions are. Maybe I have no predictions in such states. Maybe that's a philosophical question. So maybe I set those values to 0 on the diagonal here too. I just don't care about them. This could also specify like degrees of how much I care. Like I really care about this one, I kind of care about this one, I just a little bit care about that state. All of that's totally encodable by setting this equal to some like big constant, 0.9 and I don't know, 0.08 and 0.02, something like that. So that's D. For most of this talk, when I talk about D, I'm just going to assume that D is equal to the visitation distribution under my target policy. I'm going to stay actually totally in the on policy case for this talk. A lot of this extends to off policy, and it's actually where most of it stems from, but it's easier to talk about in the on policy case, so that's where I'm going to hang out. Yeah, I wrote this thing as if there was some value that's not equal to 0 outside of the diagonal, and that totally could be the case. What this is specifying then is there's some degree of error that is shared between two states, state I and state j here. So maybe as I decrease the error in state I, I'm simultaneously decreasing the error in state j. That might be the case if we have some degree of generalization. So maybe I have some state 1 here is actually this concatenation of all these states. Some other state 2 here is a concatenation of these states. And as my agent is running around in this region, then maybe I'm going to be affecting the error, affecting the quality of the prediction of multiple states at the same time, state 1 and state 2. We're going to revisit this quite a bit. It's actually kind of the point of the talk, I suppose. And this is me acknowledging that I abused notation by making D a function of 1 parameter versus 2 parameters. That wasn't really that important, I suppose. So the first thing is this idea of learnability. Rich introduces this topic of learnability in the textbook, chapter 11. And he gives these two MDPs as this sort of example of learnability. So this is, I just directly copied this from the textbook. I did make some slight alteration here where he encoded this as having a weight, whereas I encoded this as a feature vector, or feature scalar, I suppose, in this case. But otherwise no different than what he said. And what's interesting about these two MRPs, rather, not MDPs, I'll probably keep saying that by mistake, is that they both encode the same data distribution. That is, I showed you a sample of some trajectory, some set of data I could have received. And this trajectory is equally likely to have come from either of these two MRPs. And to kind of wave my hands to show why, my feature vector is always 1 in this case, and also always 1 in this case, no matter what state I'm in. And also I have a 50% chance of seeing a reward of 0, 50% chance of 2. Likewise, I have a 50% chance of 0 here and a 50% chance of seeing 2 here. This one, to show that's true, requires some conditional probabilities. I'm going to skip over those for the sake of time. Rich goes into a lot of detail in the book on this. And the two questions he brings up is, a couple of the questions he brings up is, what things can you learn from this data that we observe? For instance, something I can't learn is what state I'm in. If I'm an agent and I was just dropped into this MDP, I can't see the state. I don't know that I'm in A, B, or C specifically. I just know that I was dropped into one of these two MDPs. And I'm observing a 1 all the time from my features. And I'm observing a reward of 0 half the time and a reward of 2 half the time. So I have no clue what state I'm currently in. Now I can choose to take my one action and make an observation. So let's say the agent is here and it doesn't know it. And it takes its one action and it's randomly sent either to C or back to B. And it's going to receive a reward of 0. So now the agent knows, oh, I must have been in state B. I know that for sure. I was in state B. But with 50% probability, I'm now in state B or in state C. So again, I actually don't know where I am now. And that's going to be forever true. We also don't know how many states there are. You can imagine up here we have some like an initial state. This agent is always stuck here. And with 50% probability is transitioned into the left MRP, 50% probability is transitioned into the right MRP, and like 0.25 on each of these transitions. So it's equal probability to go in either of those two states. Now I have no idea if the MDP that I see for the rest of my life after that first state has 1 state or 2 states, because again, that information is not even kind of encoded in the data distribution I actually observe. And so all of this is just kind of pointing out this definition of learnability, that given the observations I see from my MDP or MRP in this case, what things can I learn? Rich goes on to point out that the value error, the mean squared value error, is not a learnable quantity, but the parameter that it minimizes is. He gives some good arguments for that, but I'm actually going to skip over those at the moment. Instead, I'm going to talk a little bit about the mean squared Bellman error and talk about how this is not a learnable thing. By the way, all of these, I had a hard time getting overlines in PowerPoint to work, so I just skipped them. But every time I say BE or PBE, I really mean mean squared BE or mean squared PBE. Yeah, so these arguments come from Bruno Scherer in his work in 2010. I'm just gonna, let's see, where do I want to start? And so the argument that he's making is I have all of my states, I list all of my states here, and I want to partition the states. I'm partitioning them into K states, where the V pi of these K states is in the span of my features, meaning I can represent V pi. That's really what I'm trying to say. And SL here, I can't represent the true value function for those states. And so I've partitioned the states into the ones I can represent, the ones I can't represent. And if my transition dynamics has this block triangular matrix structure where each one of these four things is a matrix, then I end up with value functions that look like this, according to the Bellman equation. Yeah, that's actually a really good comment, Chaba. Identifiability is what a lot of the rest of the statistics literature calls it instead of learnability. I went with learnability just because I was building off the textbook, but yeah, very good point. Yeah, so we have these equations here where v pi k depends exclusively on vk depends exclusively on vk, which I can represent perfectly. So this means that this thing in the limit, I could absolutely find v pi of sk given enough data. This thing depends, v pi l depends on knowledge of v pi l, because that thing is not representable with the, I'm not going to be able to learn this quantity. And the argument that's made about the mean squared Bellman error is that the mean squared Bellman error balances between these two things. So it tries to learn a v hat k here, such that it balances between the error of this, making this equation true, and the error of this part of the equation, making this thing true. And this is just always going to be some irreducible error. I can never reduce this quantity. So in the Bellman error, mean squared Bellman error case, I'm just balancing between the two things. In the projected Bellman error case, the mean squared projected Bellman error, this is another way I could have chosen to pick my v hat. And in this case, I'm only going to care about this top equation. The thing that I can represent perfectly, let's represent that thing perfectly and ignore what's going to happen here. So some arbitrarily bad error might happen in that v hat l case, but I don't care. That's sort of the claim that the mean squared projected Bellman error is implicitly making. And so this brings up a question. Maybe these things both have the same degree of error, same amount of error, and it's just a question of balance. How are these two things balancing that error? And that's what the rest of the talk's going to be about. I did a lot of math here because I thought some crazy idea that I was going to be able to get through it in time. Of course, I'm not going to. So I'm just going to skip to the punchline and tell you what it says. So I wrote out the mean squared Bellman error here in this norm form. So we're T there, that is the Bellman operator. Did a whole bunch of stuff, and then ended up down here with what looks to be the mean squared value error. Only instead of D, I wrote this nebulous M thing, and M is that. K, I didn't tell you what it was. I would have if I walked through the algebra. So let me write it here. K is I minus gamma P. Yeah, that was it, actually. I minus gamma P. And so now we have this weighting here that's no longer necessarily a diagonal matrix, but importantly, it is positive definite in the case that D is a steady state distribution over the policy. And Shockneck 2003 gives a little bit more motivation why this thing is positive definite, because it's not necessarily obvious. But it is important because it does mean that we have a unique V hat here that minimizes this norm. So to give a little intuition about what M is saying here, because this is no longer a diagonal matrix, it's kind of hard to visualize, is we have this blue part, which is the diagonal. I'm going to go ahead and just say, let's say I applied SVD, so I've broken this thing into rotations and scalings. Then what this matrix is going to do is it's going to stretch us out over some of the states, where orange here is our error, our mean squared value error. And so as I move around in state one in parameter space or in error space, it's magnifying my total error by, say, 2, it looks like, in this case. So any small amount of error in state 1 means my total error is twice as big. Any small amount of error in state 2 is going to be comparatively half as large. And then these off-diagonal things over here, things they contribute is this sort of like rotation or shearing. So that now if I'm moving around in state 2's error space, I'm also jointly going to be moving around in S1's error space. And that is to say, this angle here is no longer orthogonal, no longer 90 degrees. So I'm not just only affecting the error of one state, I'm affecting the error of both states as I'm moving around in just the space of one state. And it gives kind of an intuition on what this weighting here is doing to our space. Yeah, so I kind of breezed through that. Were there questions that popped up from that? The next thing I talk about is going to be largely the same, just for the projected Bellman error case. Okay. And just like the Bellman error, I thought I was going to get through so much math that I'm clearly not. So let's talk about what I was going to say. So I wrote out the mean squared projected Bellman error. It's the exact same as the Bellman error, except that we have this projection operator here. I actually kind of like the way I wrote it on the next line even, which shows this thing looks a lot like that mean squared Bellman error I wrote just a minute ago, and now I'm just projecting that error. And this projection is really should have been written with like a subscript D down here as a weighted projection. And it projects my error into the space spanned by my features. That's all that's trying to say. Great, so I do some steps. I also skip some steps. And I get down to here, where again, I'm measuring my mean squared value error. So I do still have the same error that I had in the mean squared Bellman error case, except that I'm measuring it over a totally different space, topological space here. And that topological space is clearly this very simple but symmetric matrix M. That was a joke, this isn't clear. M, in this case, though, is positive semi-definite because of this key matrix right here, which is in general positive semi-definite. You might recognize this thing. It's better written as C inverse, or often written as C inverse, as this expectation over this outer product of our features. It's our feature covariance matrix. And so, as Chapa brought up, we have this question of identifiability. In this case, oops, I'm really skipping, I'm sorry. Go back. In this case, because this thing is now positive semi-definite, that means this thing is no longer a norm. It's now this thing called a seminorm. And that implies then that my mean squared projected Bellman error is going to equal 0 for v hats that are not equal to v pi. And in fact, there's infinitely many of these things. In the case that this is positive semi-definite, it's not guaranteed this is positive semi-definite. In fact, a lot of proofs assume that it is positive definite, and we just move on with life. But there are a lot of instances where it isn't. And so there's going to be infinitely many cases where our projected Bellman error is 0, even though we haven't found the optimal value function. And the problem with that is the weights, the value function that we learned, the thing that we actually converge to, is not going to be known ahead of time. It's going to be a function of the data that we receive, the order of the data that we receive, a function of the optimization algorithm we choose, etc. There's a few things we can do to solve this problem. For instance, if you just allow a little sloppiness of notation here, I can add a regularizer in there, make sure this thing is always positive definite. And a couple of other options that we can take, I'll kind of touch on a little bit in the next 5 minutes. Yeah. But in general, the mean squared projected Bellman error, I guess the claim that I'm trying to make here is it actually kind of has the same problem as the Bellman error. A different problem, but the same conclusion, and that is actually not identifiable. We're not going to come to the same set of weights for the same data distribution. And so, yeah, the next thing I kind of want to talk about is other options, other things we could do. And I really like the projected Bellman error, and I didn't want to diss on it too much. So I want to talk about it as this sort of building block. Maybe I shouldn't have skipped yet. Sorry. So yeah, this is my value estimate. And the thing I'm trying to draw, this sort of shell here that I drew, this is a like a surface, a two-dimensional surface in three-dimensional space. This is, as I'm moving around in weight space, I move around this three-dimensional error space. When I apply the Bellman operator, I'm going to end up at some point that's off of my shell, off of that surface. And when I apply the projection to that thing, I'm going to project it back to the nearest point on my surface. And even though I didn't quite draw it like it, that's an orthogonal projection, so that's going to be a right angle. And then the punchline I was getting to, so we can apply the Pythagorean theorem, and we end up with our mean squared Bellman error here. This is our mean squared projected Bellman error. This is something I'm calling the mean squared projection error. This is the error due to how far we had to project to get back to our features. And I'm calling this a PBE building block because you can kind of view this as we have some objective, which is saying, assume that I'm given really good features, or good enough features at least, and I have no control of the features I was handed. This is how good of a value function I can learn, or this is the value function I want to learn. This sort of thing is saying that if I had control over the features I was learning, maybe I would want to try to minimize that distance by creating, learning, generating, whatever word you want to use, finding features that bring this distance closer to the point I was projecting, or the point that that took me off of my surface. So I want to move my surface towards that point. I wrote this as a plus here only because I wanted to make it necessarily equal to the Bellman error and claim that maybe the Bellman error is this like joint optimization thing or multi-objective optimization thing that is concurrently trying to solve the projected Bellman error issue while also trying to solve this projection issue. If I were to just plug the Bellman error into, say, a neural network as some example, it's not really me erase, as some example of a learning system that's learning the features jointly, then what this is kind of saying is give me features that do a good job of creating a value function while simultaneously give me features that do a good job of bringing my surface, bringing the things I can represent towards the data I'm observing, which is this Bellman operator. It's not letting me erase, so I'm sorry this is getting really messy. Oh, there it goes. I guess I was done anyways. I don't really have time to talk about the TD error. I'll just say that we could continue adding on to this building block by talking about this mean squared TD error that no one really seems to like very much, probably for good reasons. And if you had agency over these sort of variance terms that pop up, you could even consider learning features or learning a policy, depending on where you're injecting that agency, if you will, such that we actually penalize being stochastic. So this is capturing stochasticity in R. This thing, let me write that. That is I plus, or sorry, that is not I plus gamma. That is R plus gamma V prime, which is R plus gamma P V, the hat there. And so this thing is capturing some stochasticity in our reports, some stochasticity in our transition. And so my claim here is if we had some way to give our agent agency over controlling these two terms, maybe we could be penalizing how stochastic our observations are. So if I was in some grid world, let's call it a windy grid world. There's wind down here in these states. The agent starts here, it wants to get here. Maybe instead of running around in these states and collecting reward and getting to the goal, maybe it chooses a policy that totally avoids those states because it's being penalized for any amount of stochasticity in its observations. Yeah, I don't want to make super strong claims about that because that's totally an unvalidated claim whether or not that's something we want. But we've been discussing stochasticity and determinism in our agents recently. That felt somewhat related to me. So I'm just going to end with a few things of what's next. I kind of gave you an overview of the literature as I see it. I made a couple of judgment claims and calls in my way of presenting it to you and my way of compressing it. But largely, I was mostly just reporting on some of the conversation that's happened in the literature. Here's a few things that I kind of want to do as a step forward after having done that. We have this fun mean squared kernel Bellman error coming out of Li's lab. It's really similar to the mean squared Bellman error. It just has this weighting between states that comes out of a distance metric, the similarity metric between any states. So I imagine it's going to come out to be a very similar norm. We're going to have this sort of v hat minus v pi squared. We're going to have an m down here, and this m is going to have some kernel weighting between our two states, any two states represented as a matrix. I haven't looked, but I imagine it can be written that way. So it'd be kind of fun to keep unifying things in the literature with that. I mentioned one manipulation on the mean square projected Bellman error, adding a regularizer. Our TDRC work that Sina presented a few days ago, we did that. We played with it a little bit. We proposed a couple of optimization algorithms on this regularized mean square projected Bellman error case. we showed that there's a unique solution to it, so it's now identifiable or learnable, which that's good. That made us happy. The thing that it learned was the minimum of the, or was the TD fixed point. So that was cool. There's probably a lot of other manipulations we could do, other restrictions that we could add to this. As I pointed out, there are infinitely many solutions to mean square projected Bellman error. Our regularizer happened to choose one by encoding this implicit, this bias that we want simple solutions, if you will, or solutions where W is near 0. But we could totally index into those infinitely many solutions using other heuristics, like W's that have lower stochasticity, going back to that claim, or W's that encode other properties that we like. Yeah, I mentioned early on that D was a steady state distribution, state vegetation distribution over the target policy or the on policy policy. There's lots of different Ds we could choose. And yeah, we should investigate those, like emphatic weightings or the behavior policy distribution, target policy distribution, so on and so forth. And finally, I kind of hinted at this idea of what if we just plugged these different building blocks into a neural network or some other feature learner, feature extractor? What would happen? What would come out of it? The answer is I have no idea. I didn't think of it until like 2 hours ago when I was putting these slides together. But I think it'd be really interesting to look into. And that's all I've got. These are the works that I used. I know that was kind of lightning fast. I'm sure there's questions.
I have a question.
Yes.
As requested. Yeah, so as when you're talking about the projected Bellman error and you're talking about there's all these solutions that have 0 errors, I was wondering, isn't that a feature rather than a bug, right? Like if multiple solutions have the same error, that means that they basically represent the same value function, right? So even though they're different weights, because your feature matrix doesn't have full rank, they represent the same value function. And so all of, and up to like weighting, right? So maybe there are some 0 weight states where it differs, but who cares about that? So it seems like that's a good thing, right? To be able to converge to any of those without requiring like a particular weight vector, because like who cares about the weight vector anyway?
Yeah, that's a really interesting question. I guess that I haven't thought about it carefully, so I might say something really stupid now. But it seems like that sort of assumes that there is that we are handed really good features or good enough features that we're going to be able to represent well the states that we care about, and that all of the states that we care about can be represented. Whereas maybe there is a weight vector that we particularly want, but it's one of those infinitely many, and it's one of those infinitely many because our features are really bad at representing some state that we like. So I want to draw a grid world again to try to...
Right, but what I was saying is that all of these weight vectors in the end represent the same value function, right? So why should you care about one weight vector, like in any possible situation, right? Like regardless of how good the features are or anything. If they represent the same value function in the end, why do we actually care about the weight vector?
So I think, let me see. If I have some policy that visits, say, these states, but for whatever odd reason, I have a feature representation that only lets me represent these states and not that corner state, for instance, then my point was we could have infinitely many weight vectors, one of which represents this really, really well, perhaps many of which represent that well, but hopefully at least one that represents that one state well, assuming we have some generalization and whatnot. And a lot of other ones that maybe represent this state well, or some that represent this state well. And so if we have bad features, we're kind of at a loss. There's not much that we can really do. But if we have some prior knowledge, maybe we could bias our solution towards states that we are more likely to see or care about. I don't know if that...
I wonder if what you're saying is that the actual value function returned is the same. But I think, Andy, they're not the same, that they're actually different value functions, but according to your loss, they're equivalent. Like they give you the same loss, but they're actually different value functions.
Totally different value functions. Yeah, I agree.
But I think Roshan was saying that if they're the same value function, then who cares? And I agree with that point, actually.
Right. Okay, yeah, you're right. You're right. I think I was answering the totally wrong question there. I agree. If it's returning totally the same value function, I don't care what the weights are.
Okay, so you're saying that there is some information in the unprojected value function that is being lost when you do the projection, and you want to somehow use that information to sort of find a better value function or something.
Exactly. And maybe I have some inductive biases that can help. I don't know if that's true. That's quite possibly not true. Or maybe there's some other things I can do to encourage better features. There's a whole lot of work on feature learning recently that I really need to go read and understand that I think will be very related to some of these claims I made.
Okay, thanks.
I'm going to jump on what Roshan is saying. Maybe one thing that is kind of seems maybe true is that this PBE is going to be non-identifiable, as there's going to be like lots of different solutions. If your phi is like overcomplete, like you have more features than you have states, let's imagine, and then that thing's going to be low rank. And then inverse doesn't mean, maybe we'll talk about pseudo-inverse or something. But that's the setting where you wouldn't, all the value functions would return the same predictions. You would just have extra features. So then, whatever. But then the other situation where your features are, like let's say smaller, they're aliasing things together. When would we expect this M not to be full rank?
That's a good question. We have a few cases where M is not full rank in these sort of pathological examples that we see in the literature sometimes. Like, I'm trying to remember. I was going to say Baird's counterexample, but that's actually an overcomplete example. I'm at a loss for an example at the moment.
I definitely believe it's possible, but yeah, I couldn't think of one.
Yeah, I'm at a loss.
Just make that happen by putting zero weights and too many states or something like that. I think that that's an easy way to. It's almost a cop-out.
A cop-out way, yeah.
Otherwise, like if phi is full rank, then it's like, oh, okay, like I don't know.
Yeah, I agree. As soon as phi is full rank, then this whole argument about the identifiability of the projected Bellman error totally goes away. And now it's just completely a question of if my features are good enough.
If we're just having a discussion right now, really interesting stuff, Andy. Anyway, I feel like one of the things actually about the identifiability for the projected Bellman error is that maybe in fact it's the other way around. Like we have identifiability problems if we let things be too general, and then we'll put in some kind of restrictions to make things identifiable. I think if the projected Bellman error is making the restriction very stringent, and maybe it's too stringent. So maybe it's not just, there could be identifiability problems sometimes, but sometimes I also wonder if we have solved the identifiability problem by restricting things too much. And the reason I think that is because of Li Hong's work recently about this mean square Bellman error and how he's reformulated as like this min-max problem, and that with one particular setting where you approximate that min-max by using a linear function for one part of the min-max, that gives you the mean square projected Bellman error. Mm-hmm. So sort of saying if you did this really simplistic approximation, you get back the mean square projected Bellman error. Simplistic is too strong. If you did this linear approximation, you get back the mean square projected Bellman error, and then otherwise you have something more general. There's probably some in between where we go from full mean square Bellman error to mean square projected Bellman error.
That's totally true. It's actually part of one of these works that I completely left out. I don't know why I'm going through those slides to find it. But yeah, Bruno's work here also talks about a different way of trying to unify the mean squared Bellman error and the projected Bellman error. And he does so with this oblique projection perspective, where instead of just doing orthogonal projections like the mean squared projected Bellman error does, we could also consider projections at different angles, which is not the same as what Li Hong's work did, but I do think it kind of comes to a similar goal of having this spectrum, this range between the Bellman error and the projected Bellman error.
I have another question, actually.
Yeah.
I really should understand Rich's counterexample, or whatever we're calling it, example of when Bellman error is bad. But I remember the last time I went and looked at it, I didn't really understand the identifiability problem. So if you don't mind telling me, what's the problem? So I mean, I don't care what the underlying MVP is. My goal is to do value function approximation. So in these two, if I see that data as my value function estimation is going to be equal, right?
See that data in the value function.
Or am I wrong about that?
Yeah, you are. Yes, that is not correct.
Okay, okay, good. That's all I
I had to unwrap it in my head a couple of times. So yeah, I did skip a few slides here just for time's sake, but they do kind of dig into this a little bit better. And so we have these two MDPs that Rich gave in the book. And here I'm just looking at the mean squared value error, but pointing out that the mean squared value error is different for each of these MDPs for the, I didn't write this, but for the same weight equals 1 here. And I guess just to be complete, V hat is phi times W. Okay. And so for the same given weight, I have totally different value errors. And so then the claim is this isn't learnable because given the same data and the same stream, I'm going to get totally different measures of the accuracy of my value function. The case for the mean squared value error, the reason why this is okay is because the mean squared value error can be written like this. Mean squared value error is equal to the return error. Return error is purely a function of my data, so it's definitely learnable, plus, it's moving on me, plus some variance term. And the important part is this variance term is not a function of W. And so if I want to take the derivative of this with respect to W, that thing goes away, and I end up with a derivative there. And it turns out my minimum is the same across both. I'm totally waving my hands here, but that's the gist of the argument. And so the W that I get from minimizing the mean squared return error, which is a learnable thing, is also learnable and is the same W that I'd get from the mean squared value error. So therefore, the W that minimizes the value error is a learnable quantity. Going to the Bellman error, that's no longer true. Neither is the Bellman error learnable, nor is the parameter that minimizes it. And in Rich's example, what ends up happening, it's kind of what I was trying to get at with this thing, what ends up happening is this V hat K, that is, say, this state. It could be either of the two, but let's say that's state B here. And this V hat L, this thing that I can't represent, oh, that one will be the other one, so that'll be, I don't know, pick some other color, C, oh, that's sparkly. And so the Bellman error is going to try to balance the error between these two things. And so when I'm in this case and I can represent it perfectly, I'm going to get to one weight vector. When I'm in this case where I can't represent everything perfectly, I'm going to get a totally different weight vector. And that weight vector is determined by what states I can and cannot represent and trying to balance between them. As again, hand waving a little bit, mostly because I don't have slides built to walk through the mean squared Bellman error, but I think that was the gist of the argument. I don't know if that made it any more or less clear. Perhaps less clear, and that's fine.
I feel like I'm monopolizing, so maybe I should stop. But I feel like one thing I find confusing is that identifiability is usually, here's my problem, and now when I have non-identifiability, you say I have multiple solutions, and now I need to figure out which of these solutions is the best solution or something. But this is almost starting the other way around. I have one solution, and I have two possible problems I could have started with, and I'm not grokking it well enough. I should go understand it. I'll do that on my own.
Okay, since someone else is asking a question, I'm going to ask this thing that I really wanted to ask. So I know you said that you didn't really consider like what you would do with these value functions, you just want to learn them. But you're kind of implicitly making this choice of minimizing mean squared error. So looking forward a bit on what you can do with these value functions. If somebody gives you a value function and tells you that its mean squared error is low, averaged over all the states, what can you do with it, right? Like you don't actually know that error is low everywhere. You know that you can have a giant error somewhere, but less error somewhere else. So why mean squared error in the first place?
Yeah, that's a really good question. Let me go here. I cross that out. Great. I don't know why I'm still using the sparkly one. Yeah, so this mean square error that you're pointing out is completely determined by this D, and if the D that they've chosen, that some person who's chosen, they say this has a really low error for this particular D, and that if that D is not the D I care about at all, then I'm in a lot of trouble potentially.
Let me interrupt there. So I get that the D is sort of a weighting, right? It's telling you how much weight to assign to different errors, but it is still allowing you to trade off errors in one state for errors in another state, right? Just there's some weighting involved. But what I was thinking is like, for example, I was thinking of like infinity norm errors, where you guarantee that error is good in every state or something like that. Right. So why are, like, I realize that in statistics we use a lot of mean squared estimation just because of the nice geometric properties, because, you know, yeah, linear algebra. But in practice, like in terms of utility, like why is it useful to have a small squared error rather than, let's say, a small infinity error?
Infinity error. I see what you mean. In practice, why does it matter? I guess one somewhat cop-out answer is the mean squared error can be decomposed into bias and variance. So if we know that we have an unbiased estimator, then we know our mean squared error is only due to variance. And so it's giving us a metric of sort of how wrong we are in the states where we are generalizing too much, or how much variance is in the underlying MDP. There's nothing we can do about that. Otherwise, I'm not sure I can answer. I'm not sure why to say we care necessarily about squared errors versus infinity errors or versus any other arbitrary norm.
I guess it's an acceptable answer to say that you minimize the error that's easy to minimize.
Right.
So, yeah.
But is this easy to minimize?
Right. That is an awesome question. It's very hard to sample. So then we have all these proxy objectives to try to minimize it, which suggests that no, maybe it's not that easy to minimize. I think we've been spending, what, like 30 years trying to figure out how to minimize it and still trying to.
So I guess it's easy to minimize the error that lots of people have spent time thinking about how to minimize or something like that.
It's popular. It's being popular. Which is a very bad reason to work on that. But yeah. Actually, I wanted to ask a question about this decomposition. So you had this identity where the bellman error squared is equal to projecting bellman error squared plus this other error squared. Point. Yeah.
Yep.
And so if I look at this, so this PE thing, projection error, I guess.
Yep.
But it's like, it's kind of missing that, like, the bellman operator first left the space, and that's why you have to project it back. But anyways, so that's the unmeasurable quantity, and so maybe that's what's inherently unmeasurable if you don't have features, right?
Yep.
Like, how do you see where you go if you, like, just don't see outside of your space? Like, you can only stay inside a space. So to me, the reason to look at the projected bellman error is just because that's what you see from this. Right? You just don't see the other one. So you can try, and so maybe to firm this question, like, would you agree that this is a good, like, one way to think about this, that this is just separating concerns, like writing this equation allows you to very clearly state that I have two things to worry about. Like, one is identification, when I can do the identification, and the other one is approximation. And for the approximation, I just have to, I don't know, like,
hope for the best.
Something like that's outside of the standard toolbox. So actually, like, going back to this inventing features and whatnot, I think that's like a really funny way of thinking about, like, learning features. Because all those features, like, if you think that you can invent them, that they existed, you just didn't use them, right? So then when people talk about this feature discovery, it's like, it's not so much, okay, it's you discover, your method discovers it, but they were there. You just chose not to work with them. And so then, isn't it better to think that they were there, and then you have to work out a method that uses the features, which are maybe, you know, like concisely described things, and like you have memory bounds or something like that, and that's why you were not using those features in the first place? I kind of find it funny when people talk about this feature discovery, because those features being there, it's very new to you, but
yeah. So to sort of repeat back to you, just to make sure I understood what you were saying. So we could, it's sort of like an invention versus discovery question, where maybe previous people were making the claim implicitly, I'm inventing new features, and now I'm going to use those. But really, what you're saying is you're not inventing anything. Those were always there. It just, you're discovering them for the first time because apparently you just weren't using them previously.
right.
Yeah, and so
if you take a step back and then you're just thinking about that, the whole universe of like what's possible, then maybe you can find, you know, I don't know, like more systematic ways of thinking about these things.
Yeah, so if I had all possible features, if I had the whole universe of features, then I guess in a way this term here we could sort of treat like a regularizer, if you will. It's encoding some sort of structure. I only care about the features that make this projection small. And it's still not enough because, of course, then what features am I throwing away? I want to keep all of them. So I would still need some other thing. I'm just going to write an L2 norm just because I'm not thinking, don't want to think too hard about what sort of things I want to encode. But maybe I'm trying to balance between some simplicity thing, like I want to get rid of some features because computationally I just can't handle that many features. But at the same time, I don't want to throw away too many features that suddenly I lose this ability to represent the data that I'm receiving. I guess, was that an answer to the question?
Sorry, I had a question, yes.
The other thing, the other obviously bad idea, because random generation of features is an intractable problem. But I guess the other way I was kind of thinking about this is, if I was inventing features, if we're willing to entertain that idea that that's possible, then this projection thing sort of gives me an objective for doing that. That as I generate a brand new feature randomly, who knows where that comes from, then now I have some way of measuring its utility. It's useful if it brings my projection sort of distance closer to the data I'm observing. Yeah, I think that's all I had to say about that.
I just want to say one thing about this identifiability thing. I just want to look to the book and realize that's why he doesn't use the word identifiability, because it's not an identifiability problem, I guess. I keep confusing myself about that. It's about the fact that you can't optimize it if you don't have the NDP. It's a valid example for that, I guess.
Okay.
Also, does anyone else also have a crazy rainstorm outside their window right now?
Yeah, it's just passed.
I hadn't even noticed.
Was supposed to come later. All right, guys, I gotta go.
Thanks for the questions.
Thank you.
If there are no more questions, then let's all thank Andy for the interesting talk.
Thanks, Andy.
I have the pizza? I only heard the word pizza, but now I want pizza. Pizza! Pizza!
We were been planning to go bike ride to get pizza for fun, and then this happened. But it'll stop soon.
I don't see why a little water is going to stop you from getting pizza.
Just stop us from enjoying it as much.
Yeah, exactly.
I was just going to stay here in case other people want to talk about this.
Yeah, I'm still fixating a little bit on this identifiability versus learnability thing. In my head, I had totally mapped those to being the exact same thing, but you're right, they are very different. One's about the underlying problem that we just don't have access to, and the other one is about what feature or what weight vector we're going to converge to, how many we're going to converge to, could converge to.
Yeah, I guess even if I were to, yeah. So here, even this just sentence. This limits the mean square Bellman error to the model-based settings. Like, that seems to me like all he is saying is a limit to model-based settings. Maybe that's not the same thing though. But yeah, I think that's a valid argument that we'll never be able to perfectly optimize the mean squared Bellman error. But I think we'll be able to do that in-between thing where we optimize some approximation of it.
Mm-hmm. Yes, we definitely can do the in-between thing, since the projected Bellman error is some in-between thing. It's one of the extremes.
Nice job, Andy. You managed to draw at the same time, and apparently had lots of things pre-drawn.
Yeah, it was. I was practicing with this a bit. It worked pretty well with PowerPoint, but I kept getting into this weird situation where I rested my hand on the screen while I was drawing. It would be like non-deterministic where the pen would actually draw, and then it would start like zooming in on me, and all sorts of chaos happened. I realized there was no way I was going to be able to manage that, so I ended up getting like my computer propped up in this weird position, so I was like drawing from a distance to keep my hand off of it.
Okay, I'm gonna have to go now.
Yep. Enjoy your pizza.
Andy, so you said that MSCB has multiple solutions, multiple minimums?
Yeah. Yeah, so the reason that happens is because of, I'm going to overdraw, because of this term here. What happens is we end up with this semi-norm where basically we have some measure of our error, this measure of our error, and this thing is going to be 0 for some cases where that inside vector is not 0. So this is not true. And in general, a semi-norm means that I have some vector x. This thing is a semi-norm. If this equals 0, there exists, I guess maybe I should say, if there exists some x not equal to 0, where this thing is 0. And you get a semi-norm every single time this thing is positive semi-definite or is not full rank.
I see. So which one does TD converge to?
That's a good question. Bruno Scher has a lot more insights on this that I didn't quite follow in his paper. But in general, what we have a tendency to do is instead of just taking an inverse here, we do the pseudo inverse there. And the pseudo inverse specifies some degree of structure. And it's really hard to think about. If I call this the C matrix, like we normally do, then the pseudo inverse is going to say, I'm looking for some C transpose C inverse C transpose. I'm looking for some matrix that, and that is hopefully going to also be full rank. And that is going to index into those infinitely many weights and choose one of them. Well, what that structure is kind of hard to intuit. You can view it as some sort of like regularizer, some sort of heuristic we use for indexing into those.
Oh, okay. One thing I wanted to ask was, does the null space of this matrix tell us anything?
Good question. So I guess the null space of this matrix would tell us what states we won't be able to represent well. Is that true?
What errors are not going, like what errors are going to be seen as 0 under this norm, right?
Yeah, and it would tell us, I guess, what principal directions, which may be along a state, but it also may be some combination, some complex combination over states. But what principal directions along which this thing could still be zero, no matter how far we move in those principal directions. We could go towards infinity in that direction, and this thing will still measure zero. So yeah, I guess that's what the null space would tell you.
And we won't care to, we don't even care to minimize those errors, or would we? Like in an actuality.
Yeah, that's also a good question. The claim I was sort of trying to make was maybe we do care about those errors. We just don't get the option to care because we can't represent them. But maybe we're in some world where we get to manipulate our features or pick our features or what have you, because we do care about those states, so we want to make sure they don't exist in our null space.
Oh, okay. Okay, I was trying to relate this to the stationary distribution of the states and this principal direction of the states, but I don't know if that would work or not. If you're able to have those directions exactly orthogonal to each other, then we don't care actually about the states that are being misrepresented by this matrix according to the stationary distribution, but I'm not sure.
If you look at Schachnecht's work, he talks about this a little bit. It's a lot easier to see in this Bellman error case. It's just a much cleaner matrix. But the states, if D is our stationary distribution according to our target policy or on policy, then the states where D is equal to 0 are also states where we can just omit those rows and columns, corresponding rows and columns in P in our transition dynamics matrix, and we will still end up with a full rank.
The same MSPB also, I think. The same weights.
Yeah, but it'll be the same weights, same mean squared Bellman error. And this matrix will still be full rank, even if we omit all of those. So we can have zeros along this diagonal matrix and still have a full rank matrix, is the argument that Schachnecht was making.
Oh, okay.
I imagine my wife's probably getting hungry, so I should probably get going soon. Do you guys have any other questions? Bye, doll. All right, sounds good. Well, thank you guys for showing up. Thanks for the questions.
Thanks, Andy.
Yep, see you guys later.